Okay, we are off to our next chapter here. Yesterday during lab, we did kind of finish chapter 9. And again, we talked last time about limiting reagent type problems, as we did yesterday, and a couple of examples. It really is the same sort of calculation as a basic stoichiometry problem. Again, you do have to sort of in the middle figure out which one is the limiting reagent. A reminder that you do need to do a calculation to figure out which one's the limiting reagent. You shouldn't just choose the smallest number of moles. Again, it won't always be the smallest. So you do have to take the stoichiometry into account. And so you do have to do a calculation. The reason we do determine the limiting reagent problem, our limiting reagent, is that is the one that determines how much product we can make. So once that is used up, we cannot make any more product. So whenever you're trying to calculate a yield, and we talked about a few different yields, and we did our lab, obviously our theoretical yield, which comes from the equation, you should always do it based off the limiting reagent. And the theoretical yield, again, is your maximum yield that you could get based on what you started with, based on the equation, the stoichiometry. And that, again, is like if everything went perfect, that is exactly how much you should get out. As you saw in your experiment, things don't always go perfect. You can't always get everything out. Like you still had yellow residue probably everywhere, right, on your stuff. And all that yellow residue is actually your product, right? So you kind of lost that product that you couldn't get out of your beaker, for example, or maybe your stirring rod or something like that. And what you actually get is known as the actual yield. In the case, obviously, of the experiment we did yesterday, that was the amount of yellow precipitate that was left on the filter paper. In terms of a textbook problem, the actual yield is usually given to you in the problem. They usually will tell you that. Yes, sir. Exactly. So the percent yield, which is, as we talked about yesterday, the percent yield is your actual, what you actually got when you did the experiment over your theoretical times 100%. And basically it is pretty much that. It's really kind of how close you got to, sort of getting everything out basically, or basically producing as much as possible in that reaction. That's why when we look at a percent yield, we are looking for sort of a higher number. As we talked about yesterday, we're not really looking for over 100% because that usually means that, something didn't go so right there. But we are looking for a higher number is better in a percent yield. If you had a percent yield of 10, then that wasn't so great because you kind of lost 90% of your product basically somewhere along the way in your reaction. So that's sort of the idea behind that. Sometimes people get percent yield, and later on when you learn about percent error, confused. Percent error, you're actually looking for a low number. Percent yield, you want kind of a higher number, because percent error tells you basically how good you did the experiment. So you want sort of a low percent error, how much error you had in that experiment. Now, again, in a textbook problem, or in most cases, the theoretical yield would have to be calculated, and usually it's either a basic stoichiometry problem to do so, or maybe a limiting reagent problem to do so, like we did, I think, in that last example. But usually in most problems, you will have to calculate the theoretical yield. The actual yield, like I said, is usually given to you if you're asked to calculate the percent yield in a textbook problem. Remember, to know whether or not you need to do sort of the limiting reagent step is the key question is, do you have enough information given to you in the actual problem that you could just directly get moles of each reactant? So that is the key. Whatever units they give you in terms of the reactants, is it possible based on what they gave you to just simply get it to moles with no problem? And if the answer is yes, that you can get to the moles of everybody, then you do have to do that limiting reagent step. If you don't have enough information to get the moles of everybody in the reactant side, then it's really going to be just a basic stoichiometry step. You don't have to worry about sort of the limiting reagent. The reason you don't typically have to worry about the limiting reagent in a basic stoichiometry step is if they give you a certain amount of reactants in a basic stoichiometry, that pretty much is telling you that is the limiting reagent. So that's usually why you don't have to worry about it. That's sort of the idea that that would be your limiting reagent. So if you could get the moles of each reactant, you should be doing some type of limiting reagent. So as we also talked about, you could do it the way we did it yesterday. You could also do it, and again, a lot of books will show you that, just two separate calculations, starting with each reactant, and basically just doing a basic stoichiometry calculation with each reactant to figure out how much each one will produce in terms of the product. and whichever one produces the least amount of product would be your limiting reagent and also your theoretical yield. So that's a perfectly fine way of doing it, and people teach that all the time. We also saw that you can also figure out through calculation how much of your excess reagents left over at the end of the reaction. Your limiting reagent should obviously be pretty much zero. It should be used up because that is the one that obviously gets used up first in there. Any questions on any of that stuff from yesterday and the day before? Yeah. Okay, so we're going to now go, I guess, where were we? 9. So we're going to go backwards again. So we're going to go to chapter 7 as we bounce around. And chapter 7, we're going to really talk about ways to classify reactions. So we talked about balancing equations, obviously, and we talked about chemical reactions. So in this chapter, we're going to talk about 2 main categories of reactions and different ways you could classify a reaction. So let's talk about aqueous solutions. So we've touched upon aqueous before, and aqueous is, again, that symbol you see a lot next to formulas, and that's the AQ symbol. It implies a homogeneous mixture, or a solution is basically what it is. And a solution is a homogeneous mixture that's really made up of 2 parts. It is a smaller part, which is known as the solute. So the solute is the smaller part of a solution. The larger part of the solution is the solvent. Now, in a lot of cases, water is a very good solvent, and the solute would be, for example, whatever you dissolved in water. So as we talked about, there is a difference between liquid and aqueous. And again, something that is a liquid is really a pure substance. So again, if you had something like just water by itself, that would be in the liquid state. A reminder, the aqueous is also a liquid state, but it is a mixture, which means there's 2 or more things in that sort of solution. So if you took, like we talked about earlier in another chapter, if you took the water plus the solid sodium chloride and you put them together, again, the salt would dissolve in the water and you would get that sodium chloride solution that's aqueous. In terms of the solute and the solvent, the solute is the sodium chloride in this case. The solvent would be the water. How do you know what the solute is when you look at a solution? It's pretty simple. The name of the solution is the solute. So if you had a potassium chloride solution, potassium chloride would be a solute. If you had, like we have here, a sodium chloride solution, sodium chloride would be your solute. So really the name of the solution is the solute. I would also say that probably 9 times out of 10, if it is an ionic compound, the solvent's probably going to be water. Water is a really good solvent for a lot of ionic compounds. Why is water a really good solvent for ionic compounds? As we know from bonding, water is a polar molecule, which means that it has a negative side, which is the oxygen side, and it has a positive side, which is the hydrogen side of water. So that works really well for sodium chloride or really any ionic compound, because when sodium chloride goes for a swim, it will break apart into a sodium ion and a chloride ion. And what's going to allow something like solid sodium chloride to dissolve in water is the water molecules will basically surround the ions. So the oxygen side of water, which is more negative, would be attracted to the positive ion here, while the positive side of water would actually be attracted to the negative ion, which would be chloride in my example here. And that is essentially how you get something to dissolve and make a solution. The water molecules basically surround each of those ions. What that does is it prevents really the ions from coming back together to make the solid. And what it does to you sort of visually is there is a ton of water molecules surrounding each of those ions, and you no longer could visually see the ions floating around in the solution because they're surrounded by a ton of water molecules. And that's why sometimes people mistakenly think when you make a solution that it is a chemical reaction or a chemical change, and that is not a chemical change. This is actually a physical change. We're basically dissolving something in it. We know it's a physical change because you probably did on a couple of those earlier experiments in your evaporating dish. If you took some heat and heated this up, it would evaporate off all of the water molecules, and then that would allow those two ions to come back together. And in your evaporating dish, for example, you would actually see the solid return. And again, you would have the solid in its original form. You could trap the water if you're really interested in it and cool it back down, and you would have the water in its original form. And remember that a mixture, right, is two things that come together but keep basically what they are. They don't change. And that's basically what we have when we dissolve and make a solution, because it is a homogeneous mixture. Any questions on that there? We obviously help this along a lot when we dissolve something because we stir it, right? And when we stir it, we're adding energy, and we're also throwing a lot more water molecules on that solid, and that's going to allow them to pull off the ions from each other and help in the dissolving process. Also, if you can never sometimes have a problem getting a solid to dissolve, you can also heat it up, which also adds some energy and allows that process to occur a little bit easier. Now, one of the things we talked about in a previous chapter, which is kind of important in this chapter, especially when we talk about double displacement reactions, are electrolytes. And if you remember, electrolytes are really substances that when they go into, say, water, they will break apart into ions and conduct electricity. We have three types of electrolytes. We have strong electrolytes, which again, 100% break apart into ions. Most ionic compounds are strong electrolytes, like if you had a solution of sodium chloride. In that solution of sodium chloride, if you were to kind of look at the beaker of what is floating around in there, it would be 100% the ions. You would have none of the whole sodium and chloride units together. As we just talked about, basically they're going to be surrounded by those water molecules. It's going to keep them apart. We also have weak electrolytes. And if you remember, weak electrolytes, they actually mainly stay together. But break apart into a few ions. So a lot of weak acids, weak bases are weak electrolytes. So something like hydrofluoric acid is a weak acid. It will break apart into H plus and F minus. And in solution, you actually will mainly have this guy still together. You will have a little bit of those ions are floating around, but it's actually going to stay together, unlike a strong electrolyte that's just going to completely break apart. That's also why when we look at the arrows, we see different types of arrows for each of these. For a strong electrolyte, it's like a one-way arrow. Everybody's just breaking apart into ions. For a weak electrolyte, it's really a two-way arrow, where everybody's kind of staying together mainly, but we will have a little bit of people going to the other side. We also have non-electrolytes that really don't conduct electricity, but they still dissolve. And those are a lot of molecular compounds. So even though they can dissolve, they will not break apart into ions. And because they don't break apart into ions, we don't get any electricity being conducted. So some strong electrolytes, like I said before, pretty much most ionic compounds are going to be strong electrolytes. When they go into the aqueous solution, they're going to break apart. And again, a lot of weak acids, weak bases are going to be your more weak electrolyte. So again, sodium chloride going to 100% break apart into those ions. Yeah. Our aqueous solutions always has. I guess the way to answer that is yes, acid and bases are always aqueous, and in most cases they're basically, yeah. And that's really because for something to be an acid base, as we'll talk about when we get to that chapter, and we might touch upon a little bit, what makes something an acid base is the ability to release, for example, H plus into solution and OH minus into solution. So typically acid and bases are found in the aqueous state. Now, things that are aqueous can also just be ionic compounds, like we saw there with like sodium chloride, which technically is not really an acid or a base. So aqueous can be basically anything, but definitely acid and bases are typically in the aqueous state. Yeah. Other questions? And that's also how we talked about when we did something like HCl in like the gas state versus like HCl in the aqueous state. In the gas state, it is hydrogen chloride gas. In the aqueous state, it is hydrochloric acid. So as I mentioned before, water is a really good solvent for a lot of ionic compounds. Um, but you should also think about the idea that water is not always the right solvent for the situation. So, as something we'll talk about in a later chapter, water would actually be a really terrible solvent for something that is nonpolar. But water works really well for things that are ionic. Water works really well for things that are polar. One of the things that we'll talk about in a later chapter is this idea of like dissolves like. And the idea of like dissolves like means that things that have similar sort of properties of how they deal with themselves will be very soluble in other things. But ultimately, what that means is if you have something that's ionic and you have something that is polar, that's probably going to be soluble in each other. If you have something that is polar, and you're trying to mix them together, they're going to be perfectly fine. They're going to be able to mix and interact well with each other. The one that sometimes people miss is this one. If you have something that is nonpolar, it actually will be soluble in something that is nonpolar as well. Again, they're able to kind of use the same type of interaction they use with themselves, they would use with somebody else. So these combinations here tend to lead to things that are soluble in each other, and basically soluble means that they will mix and you will get basically like a solution. You really only run into trouble when you kind of cross over to a nonpolar and polar combination. That is not a good combination. They're not going to mix. They're not going to be soluble in each other because of that. So, for example, if you took some chlorine water and you wanted to mix it with water itself or chlorine and you wanted to mix it with water, chlorine is nonpolar and water is polar. They are not going to be able to keep together for the long haul. They will really not mix. A really simple example is like oil and vinegar, right? Our salad dressing is kind of oil and vinegar. If you ever mixed it up, right, it mixes for a bit, but over a long period of time, if you leave your salad dressing sitting there, everything will separate out. And that's because oil is nonpolar, vinegar is really polar. So over the long period of time, they can't sustain that interaction. So they separate out from each other. And that's typically what we see. So as we talked about before, water works really well for ionic because it can do basically that opposite attraction, electrostatic attraction. The way that all pretty much molecules interact with themselves or interact with other molecules is a basic interaction of electrostatic interaction, positive and negative attraction. So that's why water, which has a positive and negative side, works really well for ionic compounds because there's a positive ion and negative ion. And also why it works well with polar things because they also have a positive side and negative side. And that's how all interactions pretty much occur. It's really just a basic interaction of a positive side of one molecule is going to be attracted to the negative side of another. And that's pretty much how everything interacts in terms of molecules. That process, as I described earlier, where the water molecules basically surround the ions in solution, that is sometimes referred to as hydration because you're adding water. And for simplicity, a lot of times in formulas, we just put the aqueous symbol next to it rather than all the waters that are there and stuff like that when we write formulas. So when you see aqueous, again, that is essentially what it means. You have some things dissolved and made a solution. All right. So let's talk about some strong electrolytes and some weak electrolytes. And again, this is going to be helpful for some reactions that we will see later on in this chapter. Acid and bases are strong electrolytes and also weak electrolytes. So hydrochloric acid, nitric acid, these are all strong electrolytes which will 100% break apart in solution. I'm going to give you again a list of strong acids, and it's a really good list to know because, again, if you kind of know that these are the strong acids, just by process of elimination, you'll know everybody else is weak, and you'll know it'll be more like a weak electrolyte. So the strong acids, again, are hydrochloric acid, nitric acid, sulfuric acid, perchloric acid, hydrobromic acid, and hydroiodic acid. So this list of 6 acids are your strong acids, which means, again, in context of this chapter, if you come across one of those, you could expect it to completely break apart into ions in solution. In terms of strong bases, I'll give you a list of that as well, but I think we might have talked about it. Essentially, group 1 and 2 on the periodic table is where we find a lot of our strong bases. So essentially, if you go for where lithium is, if you go where sodium and potassium, hang a right-hand turn there to calcium, strontium, and barium. If you hook any of these guys up with hydroxide, like sodium hydroxide, potassium hydroxide, calcium hydroxide, etc. These are strong bases. So again, if you see these, you would expect them to completely break apart into ions in solution. So group 1, group 2 on the periodic table that has hydroxide in them typically are going to be your strong bases. Now, like I said, almost by process of elimination, if it's not one of these strong acids, it's probably going to be a weak acid. And acetic acid, which is here, is a weak acid, and that's not negative, that's just from PowerPoint. And as you can see here, it will break apart. It will mainly stay together as acetic acid. But you will get a few of these ions in solution. And again, that is why it is considered still an acid, because it does have the ability to produce H plus in solution. It will not produce anywhere near the amount of H plus as something like hydrochloric acid would. Again, we typically will see these reversible arrows with our weak acids and also our weak bases. I would say probably the most popular, if it's popular, weak base that you come across is ammonia. Ammonia is a very common weak base. A lot of weak bases actually will have nitrogen in them. So if you see something with like nitrogen and kind of looks like ammonia-ish, it's probably going to be a weak base. And that's a good way to kind of remember some of the weak bases. But definitely if it's not group 1 or group 2 on the periodic table and it has hydroxide, it probably will be a weak base if it's mentioned to be a base. So strong acid is going to completely break apart. Strong base is going to completely break apart into ions. Weak acids, weak bases are going to pretty much stay together in solution. Any questions on that there? Now, when we talk about classifying reactions, there's really 2 big categories of reactions that pretty much all reactions fall under. Now, within these sort of classifications, double displacement and redox reactions, there are more specific ways you could classify a reaction, but they do fall under these kind of 2 big umbrellas. There really is, when you think about any chemical reaction that occurs, there's really 3 reasons why a chemical reaction occurs. The first reason is the formation of a solid or a precipitate. The second reason why a reaction takes place is the formation of water. And the last reason why a reaction takes place is there is some type of electron transfer that is occurring. Pretty much if you look at any chemical reaction, one of these 3 things is ultimately what is happening. And for example, the experiment we did yesterday, right? One of the things you made was a solid, right? So that is the reason why that reaction took place, was the formation of that yellow solid that you made. And that's how we know, for example, a reaction took place, because we did obviously make a solid that was not there when we started, right? And that's how we know it's a chemical change that occurred. So what is a double displacement reaction? We're going to talk about each of these in more depth as we go through this chapter. But ultimately, a double displacement reaction has this general setup. You could recognize a double displacement reaction by simply looking at the reactant side, and you should have two ionic compounds. So you should have a positive guy, positive guy, and negative guy. So when you look at a reaction, you see two ionic compounds, this is always the reaction that's going to take place. And what happens in this reaction, as we'll talk about, is essentially the two positive ions, they switch partners. And what that does is on the right-hand side here, it will make two new ionic compounds on the product side. And that is always what will occur when you see those two ionic compounds. We're going to just get the two positive guys switching to the other side and make that. Now, what does double displacement take care of in terms of the reasons why a reaction takes place? When you have a double displacement reaction, much like we did yesterday, one of these guys could make a solid or a precipitate. And as we'll talk about, that is what is sometimes referred to as a precipitation reaction because we made a precipitate. And another situation, one of these guys could make water or H2O. So when we look at double displacement, which again is sort of the big category of reactions, it accounts for two of the three reasons why a reaction takes place. Either you're going to make a solid as a result of that, or you're going to make water as a result of that. And again, those are the two of the three reasons why a reaction will take place. Now, what is a redox reaction? A redox reaction is what is known as an oxidation and reduction reaction. We'll talk about what that means a little later on. But ultimately, what happens in an oxidation and reduction reaction is you get the third reason why a reaction takes place. You will have some type of electrons being transferred. So the redox reactions, which again is sort of the big category of reactions, account for electrons being transferred. So between these two sort of big classification of reactions, they essentially account for pretty much why any reaction will occur. Either you made a solid, you made water, or you have electrons being transferred. Any questions on that there? Yeah. Yeah, honestly, you would probably be much easier to just look at the reactants. And the only type of reaction where you will pretty much see two ionic compounds together is in a double displacement. So if you think about the reaction you did yesterday, you had Ki, right? And you reacted it with lead 2 nitrate, right? And when we look at these two things, right, that's an ionic compound, right? Positive, negative. That's an ionic compound, positive, negative. So just by that presence of those two things, it's double displacement every day of the week. Yeah, so that's definitely going to happen. And you know, always it's going to just switch partners is always what's going to happen. This guy's going to come over here, and this guy's can come over here. Now, earlier when we were talking about balancing equations, right, we talked about the idea that you want to make sure you get the correct formulas first and then balance the equation. And that is some situation like this, which you will probably come across where you're just given the reactants and need to write the products. And people try to balance and write the equation at the same time or the formulas. So when you're trying to predict, for example, what's on the other side, you should just basically think of these guys, again, as the ionic compounds. And just think of the basic ions that make them up. So what I know from this guy is this is K plus and this is I minus. Those are really just the basic two ions that make that up. Over here, I know that that is lead with a +2 charge. And over here, even though there's two nitrates at this point, the basic unit of nitrate is NO3 minus. I am not going to be concerned at this point with that too. And what I'm now going to do is just take these two guys and I'm just going to put them together like I was doing nomenclature, right? And balance everybody out to 0. So obviously K plus and NO3 minus is +1 -1, which means when we write the correct formula on the right-hand side of that arrow, KNO3 is the proper formula. Now, when we take this guy, which is +2, and this one, which is -1, just like we did with nomenclature, I actually need 2 of the i's, right, to balance that out to 0. So the proper formula here is PbI2. And once again, these are the proper formulas that you should put on this side of the arrow, regardless of the balancing. Once you now have the proper formulas, now you can take care of the balancing and go, okay, I got like 2 nitrates. I need to put a 2 there, and then I need a 2 over here at my potassium, and now I'm going to be balanced at that point. So that is, again, definitely in this chapter where you come across this a lot. You want to make sure proper formulas, regardless of the balancing. Once you got the proper formulas, then you want to go back and make sure you balance it correctly. Any questions on that? And that's a really, really common error. So for example, somebody or a lot of people would write something like, KNO3 2 on the bottom, or sometimes Na2, Cl2, and stuff like that. So you want to make sure that you definitely just get the right formulas and then balance. Other questions on that there? But to answer your question, I would look always at the reactant side because that is the only situation where you'll have that sort of setup. Yeah. All right, so let's talk about precipitation reactions. And again, precipitation reactions do fall under the umbrella of double displacement. So double displacement, as I mentioned, is sort of the big category of reactions where we got these ionic compounds that are going to switch partners and again make our new ionic compounds on the other side. In a precipitation reaction, we are definitely going to get one of these guys making a solid, which is known as a precipitate. So a precipitation reaction is a more specific classification of a double displacement reaction. So they're both the same reaction, just I want to call this a precipitation reaction because a solid was made. So a lot of times, for example, like the reaction we did yesterday, people would call that a precipitation reaction because it made a solid. And that's a more specific classification of it. It is still ultimately a double displacement reaction, but this is another way you can classify that reaction as a precipitation reaction. So a precipitate is made from, as you saw yesterday, you can mix two solutions together and make a solid. And a solid basically comes out of solution, like that yellow that you made, right? And when that happens, essentially, for example, in the one that you did, you had in your beaker there, basically, when you mix everything together, you had K plus ions floating around, you had I minus ions floating around, you had some lead 2 ions floating around, and you had some nitrate ions floating around. So when all those guys are floating around together, there is an attraction between the lead and the iodide, and they will combine together in the proper proportion, and then they will come obviously out of solution as a solid, and that will actually leave, for example, the other ions still floating around in the solution. So when you do see that precipitate, that's a result of those ions combining together. And you can think of it like dropping out of this liquid part, right? So kind of dropping out of the solution when they combine together to make a solid. So typically speaking, when two ions come together and there's nothing else there, they typically will make a solid if they are staying together and attracted to each other and not separated from each other. Yeah. And again, that's the same idea of what happens when I talked about earlier when you dissolve something in water, like sodium chloride, and then heat off the water. When you heat off the water, the two ions are now right next to each other. That is probably the strongest attraction force you could have is a positive ion and negative ion wanting to come together. They're going to try to stick to each other. If nobody gets in their way, they're going to definitely want to come together to kind of form that ionic solid. So here is similar to the reaction we did yesterday. And then again, in this case here, when this reaction takes place, as you saw, you make that yellow solid, which should not end up in the trash can, as they say. And when we're looking at this equation here, this is essentially what is referred to as the molecular equation. And when you write the molecular equation, you basically write all the formulas as they are together. And it basically shows you what's going on, obviously, with the states of what's happening. But what is truly happening when you do this reaction is when you take this guy and you dump it in, since it's a solution, it actually is going to break apart into its ions, like lead and nitrate, like I just drew on the previous slide. When you throw this guy in there, you're going to get some sodium ions and some iodide ions. So we could actually write another equation that really describes sort of what is happening in this reaction. And what we would do is anything that is a strong electrolyte, and that should be aqueous, anything that's a strong electrolyte will completely break apart. And in this case, the lead 2 nitrate would break apart into a lead 2 ion. And in this case, we do have 2 nitrate ions. That 2 comes to the front here. And basically what that 2 says is there's 2 NO3 minuses floating around in that solution. When we go to the next guy, this also will break apart, and that 2 will go for everybody behind it. And that will give us 2 sodium ions plus 2 iodide ions. Now, when we get to the other side, we do have something that is a solid. And as I mentioned a second ago, the only way for that to become a solid or stay a solid is they're kind of together. They're staying together. And with that, we would not break this apart because this is a solid. So we would keep this guy together because it is a solid. And that implies that they are kind of attached to each other or connected to each other. They're not freely floating around in the solution. Lastly, here we have this sodium nitrate, which is a strong electrolyte, which will break apart. That 2 also goes for each of the ones behind it. So we will get 2 sodium ions and 2 nitrate ions. This equation, which describes really what is going on when you mix those 2 solutions together, this is what is sometimes referred to as the total ionic equation. Or sometimes people will call it the complete ionic equation. Couple of things about this equation. It is an ionic equation, which means when you write the formulas for ions, they should have charges. Yeah, so that's what you see here, right? Charges on everybody. Obviously, the thing that stays together does not have charges. Yeah. When you write this equation, anything that is a strong electrolyte will break apart. Anything that is a weak electrolyte, anything that is a solid, anything that is a liquid sort of symbol next to it, or even a gas in a lot of cases, will actually stay together. So much like we did with the solid here, we keep that guy together. So how do you know it's a weak electrolyte? Like I said before, probably for your purposes, knowing those 6 strong acids, and if it's not one of those, that's again a process of elimination. If you see something that's ionic, it's probably a strong electrolyte. Again, most weak electrolytes are going to be your weak acids and bases. So, that's usually what you look at in that case. For example, any questions on that there? So molecular equation, basically written like a normal equation. Everybody's formula together, balance everybody out to 0, proper formula. Total ionic equation, we break apart anything that can be broken apart, like strong electrolytes. We keep together pretty much everybody else. Now, when we look at the total ionic equation, you should be able to find ions on both sides of the arrow that are exactly the same. So if we look at this equation, I see 2 nitrates and I see 2 nitrates. Those are exactly the same on opposite sides of the arrow. I look over here, I see 2 sodium ions with a charge, and I see 2 sodium ions with a charge over here. Those are exactly the same on each side of the arrow. These guys that you find that are exactly the same on each side of the arrow, these are what are known as spectator ions. Now, what is a spectator? If you're a spectator, you're doing what? You're just watching, yeah? You're not participating, right? And that is what the deal is with these guys. They're there really just to balance out the charge. They're having a good time. They're still swimming. Yeah, they didn't get out of the pool. They're still swimming around in the liquid part. They're just kind of floating around, not doing much, yeah? They're not leading to the product that's actually being made in this reaction. So what do we do with these? We actually take the spectator ions on both sides and we cancel them out. And they should completely cancel out, by the way. You should have the same number of spectator ions on each side. So like I have 2 nitrates on the left, I should have 2 nitrates on the right. I have 2 sodiums on the left. In this case, I should have 2 sodium ions on the right. If you find yourself, for example, with like 2 sodium ions on the left and only 1 on the right, you probably did something wrong. In most cases, you probably didn't balance the equation right, or you don't have the right formula. Those guys should always completely cancel out. And when they completely cancel out, what you are left with is the third type of equation that we write, and that is, in this reaction, what is truly happening is we have the lead plus the 2 iodides are coming together to form our solid here, right? And this reaction is known as the net ionic equation. The net ionic equation is the reaction or equation that basically tells you when you put these together, this is exactly what is really being formed here, right? It's the solid that's being formed. Basically, the lead from the lead 2 nitrate and the iodide from the sodium iodide are coming together to make this solid, and that's actually the reaction that's taking place, is the net ionic equation. It gets rid of everybody who's just watching, not really involved. So why are those spectator ions? Once again, what's going to happen in this case is this lead and this iodine are going to come together to make a solid. That's going to leave our spectator ions just floating around, right? And when that solid comes out, one of the 3 reasons why a reaction takes place is the formation of a solid. That is ultimately what is happening in this reaction. So when you see a net ionic equation, that is basically telling you this is actually like the product that you're actually making in this reaction. This is the overall real reaction that's happening, is this formation of this yellow solid in this particular case. Question on net ionic equation. Also, as you can see here on the left, they are ions, so they need charges, yeah? So when you write a total ionic equation or a net ionic equation, when you write the formula for the ions, they do need to have the charges on them. They should also really have the states, and we'll talk about how you know which ones are states, what the states are a little bit later on in this chapter. Any questions on any of that there? All right, so this is pretty much what we just talked about, so I'll just kind of scroll through it here. So how do we know, for example, if we have all these ions floating around in the solution, how do we know if we're going to get a solid or not? And what helps us determine whether or not we will form a solid or not is what is known as solubility rules. So as we talked about a little bit earlier, solubility basically means something will dissolve. So if something is soluble, that means basically the 2 things will mix. You wouldn't expect any type of solid to occur. If something is insoluble, you would actually expect a solid to occur. The solubility of something is based on temperature, and there is a maximum amount, for example, that you could get something to dissolve. So even though something is soluble, for example, we'll just take a very easy example. We're familiar with sugar, right? If you take sugar and water, it will dissolve, right? If you're sitting at the table after you ordered your dinner at a restaurant, take the little sugar packet, put it in your water, it should dissolve, right? Now, if you're sitting at the table and you went to Costco before that and got the Costco sized bottle of sugar, right? And you put it in your glass of water, at some point the sugar will stop dissolving, right? It's just way too much sugar. So solubility is based on temperature. There's only a certain amount you could get to dissolve at a given temperature. But when something is soluble, it does mean it should mix, it should dissolve, everything should look the same. When we talk about solubility rules, it is broken up into 3 sort of categories. If something is soluble, we would expect no solid formed in this case. It should all mix. And what that means in terms of your symbol that you would put next to the formula is those are the ones that get the aqueous symbol. So if you look at the solubility rules and it says soluble, then you should put aqueous next to it. You should also know that it probably is a strong electrolyte that will probably break apart into ions in solution. If something is insoluble, that means that you would get a solid or a precipitate. And those are the ones that actually get the solid symbol next to them. So the little S symbol is for anything that's insoluble. I don't anticipate you probably will come across it all that often. often. But sometimes with solubility rules, you will come across something that's considered slightly soluble. And slightly soluble pretty much means what it sounds like. It means some of it will dissolve, but most people consider slightly soluble to be more like insoluble. So a little bit of it will dissolve, but it's mainly not going to dissolve is sort of what slightly soluble is. I don't anticipate you come across too much of it, but I would say for our purposes, if you did come across something that's slightly soluble, you could consider it probably to be more insoluble in that sort of vein. Any questions on that there? All right, so let's take a look at some of these solubility rules to help us determine how something might be soluble or not. First off, this is a solubility table for things that are soluble. So everybody on this list technically would get the aqueous symbol next to them. Now, if you have anything in the actual formula that comes from group 1 on the periodic table, you pretty much do not need to look any further in that formula. You should just put aqueous next to it. It's going to be soluble. So if you have something like sodium chloride, all you have to do is look at the sodium and see the sodium there, which is group 1 on the periodic table. It is soluble. There are, by the way, no exceptions, which means it doesn't matter who sodium hooks up with, it will always be soluble with it in that situation. Same thing with ammonium. Again, this is NH4 plus, not NH3, so this is NH4 plus. If you see ammonium in a formula, it's going to be soluble 100% of the time. There is no exception in that case. So again, if you see NH4 plus, that's as far as you really need to go in the formula. You could put aqueous next to it. Things that contain nitrate, chlorate, or perchlorate are also going to be soluble. I would say probably out of those three, nitrate's a super common one that you come across. So when you see nitrate, you know automatically it is going to be soluble. It should have the aqueous symbol next to it. It's going to probably break apart into ions. Now, when you get to chlorides, bromides, or iodides, so this is Cl, Br, and I minus. These guys are going to be soluble in everything, but there are some exceptions. So normally if you have chloride, bromide, and iodide, they're going to be aqueous. But because there are three exceptions, I'll actually highlight them right there, I think. The exceptions are right here. Silver, that's lead 1. I'm sorry, that's mercury 1. Mercury 1 and lead 2. If you have chloride, bromide, and iodide with either silver, mercury 1, or lead 2, it will do the opposite of aqueous. It will be insoluble, which means it will get the solid symbol. That is why if you go back to the one we did yesterday, right, we had PbI2. So that is I. It should be soluble in everything except lead. And because lead is hooked up with it, that is why we know that was the yellow solid that we actually saw yesterday, for example. Most sulfates are going to be soluble, so most sulfates should be aqueous, except calcium, silver, which are slightly soluble, and barium, mercury 2, and lead 2, which is insoluble. So pretty much sulfate is going to be soluble, except if you have barium, mercury 2, and really lead 2 for the most part. They will be insoluble. So those guys would get the solid. Everybody else would get the aqueous sort of symbol for it. Any questions on those there? Now let's take a look at some that are typically insoluble. So these are guys that typically, if you have them, will get the solid symbol next to them and will stay together. Hydroxides are going to be insoluble, but there is the exception of basically group 1 on the periodic table. Barium and calcium are slightly soluble. So basically if you have group 1 on the periodic table with hydroxide, it's going to be soluble and aqueous. But if you have anybody else, it's going to be insoluble. Carbonates, phosphates, sulfides are insoluble except for group 1 and ammonia. So these are actually the rules from the previous slide that group 1 and ammonia are soluble in everything. So again, if you see group 1 or ammonium, they're going to be soluble in everything. They're going to be aqueous. If it is not somebody from group 1 or ammonium, then it's going to be insoluble or get a solid happening here. Here is another table from your book. Again, that's basically just another format of what we just talked about. So again, anybody on the left-hand side here is going to be soluble and get the aqueous symbol. But if you have anybody on the left-hand side that is combined with one of these guys, it will be the opposite, which means they will be insoluble and become a solid. So soluble, insoluble over here. If you have anybody on the left-hand side, they are typically going to be insoluble unless you got these guys hooked up with it, which is basically group 1 and ammonium. It will be soluble. And it says, like everything else here, you need to know them. So they will not be provided for you. So you do need to know the solubility rules here. And again, I think this is the table that's in your book. So it's a good organization of it. Any questions on that? So let's see how we could use this. So for example, if we had, I'll do it here maybe. Let's say we took, let's say we took, say we took some barium, not that. Let's take some, let's take some barium nitrate and react it with some sodium sulfate. While we do the whole shebang here, predict what you get on the right-hand side, balance it, and then predict the states of everybody based on your solubility rules. So what you get on the right-hand side, balance the equation, and then figure out what everybody's state should be on the left-hand side and right-hand side of the arrows. Take a few moments there and see what you come up with. Take a look and see. So once again here, a couple things you want to look at. Maybe. So a couple things you want to look at. First off, I know this is going to be a double displacement reaction because of what I see on the reactant side. I'll go underneath it. That is a positive barium and a negative nitrate. So that's an ionic compound. That's a positive sodium and a negative sulfate. That's a second ionic compound. So as I mentioned before, that's the only place where this basically reaction occurs. So here we go. We're going to switch partners. So when we want to predict what's on the other side, we want to just basically take the basic ions. So I know that this guy, a barium, is group 2, which means it's +2. I know nitrate, even though there's 2 of them, is NO3 minus. Again, those are the basic units that make those 2 guys up. Same thing over here. I know this guy here, I'll go underneath. That's a sodium ion, which is group 1, which is a +1. And that is a sulfate, which is a -2. So now that I have basically the basic ions that make them up, remember that what we want to do at this point is kind of put these guys together, just like we were doing nomenclature. So when I take the barium, that's going to hook up here with the sulfate, that is +2 and -2, which means the correct formula I should get is BaSO4. Same thing here with the sodium, that is +1, and the nitrate is -1, which means the correct formula I should get on this side is NaNO3. First off, any questions on that there? Now that I did that, now I should be concerned with the balancing part, right? And I can see that I don't have the same number of sodiums on each side, nor do I have the same number of nitrates. So I'm going to start there. Remember, this is a polyatomic ion, so I'm going to kind of keep it together and balance it that way. So I'm going to go with a 2 there to give me 2 nitrates. That gives me 2 sodiums, which is what I need. I have 1 sulfate on the left and 1 on the right, and 1 barium on the left, 1 on the right. So now I am actually balanced. First off, any questions on that part of it there? Now that I have it, I can now use my solubility rules, right, to determine what's going to be aqueous, right, or what's going to be solid. When I look at barium, although I may not be able to find barium on my list, when I look at the second one, that is nitrate, which I could definitely find on my list. And nitrate is soluble in everything. There are no exceptions. So as soon as I see that nitrate in the formula, I know that this one should be aqueous and it should be basically a solution. When I look at the next one, I see sodium, which I could find on my list. Sodium is group number 1 on the periodic table, and that's the alkali metals, and they are soluble in everything. There are no exceptions. I don't even need to look at the sulfate at this point. I could just look at the sodium and know this guy is going to be aqueous. Yeah? Any questions on that there? Coming to the other side, again, I may not be able to see barium, but I can find sulfate. Sulfate is soluble in everything except mercury 1, calcium, and our friend barium, which is what we have in this case. So it is normally soluble, but this is an exception. So instead of being soluble, it's actually going to be insoluble in this case. And this would be the solid that we would make in this case. It would be a nice white solid that you would actually form here, kind of like your yellow solid that you made the other day. Lastly here, I look at sodium, and really that's group 1. I don't have to look any further. I know that is aqueous. If you want to look further, in this case, you could at the nitrate, which again is soluble in everything, so they both will tell you the same thing. Any questions on how to get there? Yeah. We're going to continue on here. So, questions so far, what we've been talking about here. All right, so let's take a look at a couple more examples here. So let's take the equation we just did, and I want you to write the total ionic equation and net ionic equation and find the spectator ions. For the other two, I want you to predict what's on the product side, balance it, and also write those equations as well. So give that a go and see what you come up with. So again, for these two here, predict what's on the product side, balance it, and then write out the other types of equations, the total ionic, net ionic. For this one, total ionic, net ionic, and ID some spec. See how you're progressing here. I'm going to start here just kind of finishing the equations and getting the states, and then we'll get into the other equations just to make sure hopefully everybody's on the right page. So first, obviously, we did the first one there. When we see the second one, as we talked about, the key to knowing sort of what's going to happen is what I see on the reactant side. I see a positive and negative guy, which tells me it's ionic, a metal and a non-metal. I see really another metal and a non-metal, which tells me it's ionic. So as we talked about before, that is always going to signal a double displacement reaction that's going to happen. And ultimately, it's always just the positive guys switching partners. So remember that when we want to predict what's on the other side, we do want to make sure we just start with the right formulas. So when I look at this equation here of the FeCl2, I know the iron is actually iron 2. If I did it just like I was doing nomenclature, there's 2 Cl minuses, right? Each at -1. I know the basic unit of Cl is just Cl minus. Once again, I am not at all concerned at this point about the 2 because I don't have the right formulas down yet. Here with the potassium sulfide, the basic unit of potassium is K plus. Again, not concerned at all about the 2 at this point. The basic unit of sulfide, which is group number 6 on the periodic table, is S2 minus. And again, when you are predicting on the other side or has to write formulas, that is what you want to look at, just the basic ions that make up these ionic compounds. Now what you want to do is put these guys together just like you were doing nomenclature to make sure it equals 0. And that would get you, in terms of the equation, FeCl2 plus K2S. Now when I combine my iron and my sulfide, that's +2 - 2, I just need one of each of them to get to the proper formula. When I combine my potassium and my chloride, that is +1 and -1, which means I just need to get one of each of those to get to my proper formula. First off, any questions on that there? The order is correct formulas like we did. Second step to that is now we worry about the balancing part, right? Now that we have the right formulas, we want to balance it. And to balance it, I think in this case, you actually just need a 2 right about there. And I think it should be balanced at this point. Any questions on that one there? We're going to do the exact same thing for our last one. I see a positive, negative guy, metal, non-metal, it's ionic. Positive, negative, metal, non-metal, polyatomic ion. So again, double displacement for sure going to happen. Going to switch partners. Once again, we're going to look at the basic units. So the basic unit of this guy here is lithium, that's group 1 +1. Bromine, which is group 7 -1. The basic units of this guy is silver, which has a fixed positive charge of +1, and nitrate, which is -1. Once again, now we're going to put these guys together to balance it out like nomenclature. So I'll just rewrite the whole formula here, our equation. So when I put those guys together properly, +1 and -1 gives me LiNO3. +1 and -1 for the silver and the bromide gives me silver bromide. At this point, I could go back and balance, and I'm actually balanced at this point. Everything is 1, basically, yeah? Any questions on that there? So again, that is definitely always the order you want to do it. Correct formulas, then coefficients to balance. Yeah? Now that I have everybody's formulas, I can use my solubility rules, right, to help me decide who's going to be aqueous and maybe who's going to be a precipitate in this case. I look at this, and I really maybe don't see iron on the list, but I do see chloride on the list. And once again, I do see chloride right here. It is soluble in everything except for silver, mercury, and lead. And in this particular case, that is none of them, so it's going to be aqueous, right? When I come over here to this and I see potassium, that is group number 1. That is soluble in everything. I don't even have to look any further. I know this thing is going to be aqueous, yeah? You want to look at the sulfides, you can, but you don't actually have to in this case because there are no exceptions for potassium. When I look at iron, I may not see it, but I do see sulfide. So if I come over here, sulfide is insoluble, which means it's solid, except if it's hooked up with group 1, which iron is not part of group 1, and it's not ammonium. So that means I know that this guy is actually going to be insoluble or a solid based on the solubility rules. Lastly, here I can look at potassium, which is group number 1 on the periodic table. And once again, that is as far as I need to really go on that because there are no exceptions, and I know it's going to be aqueous. Any questions on how to use the solubility rules there to do that? Now, if I come to my second one, once again, I actually see lithium, which is group 1 on the periodic table, which means it's soluble in everything. There are no exceptions. I do not need to go any further. I know that's going to be aqueous or a solution and soluble. Silver, I may not see on my table, but I do see nitrate. And once again, nitrate right here is soluble in everything. There are no exceptions. So that means that it is going to be soluble in this case. Coming to the other side, I see lithium, which is soluble in everything, and so is nitrate. So you could choose either one of those if you like, and that's going to be aqueous. And lastly, I see silver, but I do see bromide. And bromide is on my list, and it's soluble in everything except if it's hooked up with silver, mercury, or lead. In this case, it's actually hooked up with silver, which means it's not going to be soluble. It's going to be insoluble, and that would be our solid that we would actually form in this case. Any questions on how to use the solubility rules there? Yeah. Okay. So now let's take a look at the two different types of equations that we talked about. So we'll start with the first one we did. So I can go to the next page and rewrite it there. Barium nitrate, I think is what we got. Plus some sodium sulfate. And what did I go first? Barium sulfate. Barium sulfate. And sodium nitrate. All right, so we have our balanced molecular equation, right? So now what we could write is our total ionic equation. So remember, anything that's ionic or a strong electrolyte will break apart. So this first guy will break apart into a barium ion, that is +2. There are 2 nitrates, so when you do this equation, the 2 comes to the front to indicate that there are 2 of the nitrate ions floating around. Here, this 2 also comes to the front because it indicates that there are 2 sodium ions floating around. And sulfate is SO4 2 minus in this case. And basically those are the ions basically that are floating around when you dump those things together basically in the beaker. When we come to the other side, we have a solid, which the only way it could be a solid is it has to stay together. So we do not break that apart. And once again here, this ionic compound here that's aqueous will break apart. The 2 does go for each of them, so we will have 2 sodium ions and 2 nitrate ions. This again is our total ionic equation. Any questions on how I got there? Yeah. We can ID our spectator ions. They are the ions that are the same on both sides. So if I take a look at that, that is our nitrate. Again, we have the same amount. That is also our sodium in this case, that are our spectator ions. So these are our 2 spectator ions in this case. Again, as I mentioned earlier, what we do with our spectator ions is we cancel them out. And what we are left with is our last equation, which is what is really happening in this reaction. That is the barium ion is floating around and finding the sulfate ion, or the other way around perhaps. And they're going to come together to make this barium sulfate solid or precipitate, and that would get us our net ionic equation. Any questions on any of those equations there? All right, let's take a look at the next one that we did, which was, maybe I'll squeeze it right here. Iron chloride and potassium. So we had FeCl2 plus K2S, FeS. All right, so this is our molecular equation. Again, we could do our total ionic equation. So anything that is aqueous or a strong electrolyte will break apart. So that is iron with a +2 charge. That 2 means there are 2 chloride ions floating around in the solution. So that 2 does come to the front when you do this. Here we have 2 potassium ions floating around. Again, the 2 comes to the front, and we have a sulfide ion. So once again, on the left-hand side of the arrow, this is basically the ions you get when you toss them together in the beaker. These are all the guys floating around. Now we're going to get our iron to sulfide, which we, based on our solubility rules, is a solid and will stay together. Our potassium chloride is a strong electrolyte, which means it will break apart, and that 2 goes for both of them. We'll get 2 potassiums and 2 chlorides in this case. And again, this is going to be our total ionic equation, right? I'll abbreviate it TIE there for short. At this point, again, we're going to be looking for our spectator ions. They should be exactly the same. looking on each side of the arrow. So in this case, I see 2 chlorides and I see 2 potassiums, right? So they look exactly the same. And as I mentioned before, they also should be the same amount of each of those guys on each side. These again going to be our spectator ions. We again will cross them out on each side of the equation, and that will leave us our final equation here, which is again ultimately telling you what is happening. And again, in this case, it is the iron 2 finding the sulfate ion that's floating around. They will be attracted to each other and bind together and make this iron 2 sulfate solid. And that gives us our net ionic equation, which again is the formation of this solid. Any questions on that there? Yeah. Yeah, I would say in most cases they do. You can have some net ionic equations that has ions in it and some other things, but in this application, definitely with a precipitation reaction, it should always form a solid. Um, and it won't always form a solid. We're going to see a double displacement reaction where actually will make water, for example. So you can actually make other things, but definitely precipitation reaction, you should have a solid, and that ultimately is what is happening in that reaction. So that ultimately is what should be there at the end. Yeah. Yes, sir. Yeah, so for our purposes here, something that is aqueous should be broken apart, I would say. The one exception would be, again, if it was a weak electrolyte. So if you had something like a weak acid, like HF that we talked about, or like acetic acid, you would actually keep that together and not break it apart. And, yeah, and we'll see an example maybe a little later on in the chapter where what to do with that. But you would actually keep it together. But so for the most part, if you have aqueous, it's probably almost a safe bet that you would break it apart in the total ionic equation. If you see anything that's solid, liquid, in most cases, gases would most likely stay together. Yeah. Along with those weak electrolytes would also stay together. Yeah. All right, one last one here to write the equations, which is our bottom one here, lithium bromide and silver nitrate. So lithium bromide and silver nitrate. Again, giving us lithium nitrate here and silver bromide there. All right, so once again, here is our molecular equation. And if we want to write our total ionic equation, we will again break this guy apart. And really anything that is ionic, it's a safe bet for the most part to break it apart. So metal, non-metal, definitely. Lithium and 1 bromide ion. Silver nitrate is also going to break apart into a silver ion and a nitrate ion. This also an ionic compound here that is soluble, so it should break apart, lithium and nitrate. And lastly here, our solid will definitely stay together here, AgBrS. Now here, if we look at our spectator ions, we will find our lithium on both sides. And also our nitrate on both sides. Again, these are the guys just kind of hanging out and floating around. They are really not leading to any of the products that are being formed in this case. So these are our spectator ions here. We're going to cancel those out, and we will be left with our net ionic equation, abbreviated NIE. We will have our silver ion plus our bromide ion here going to make silver bromide. And again, that is ultimately what is happening in this case. And this is our net ionic equation, obviously, in this case, the formation of this solid. The answer to the question that you might have is it doesn't matter if you wrote Br minus plus Ag plus, as long as they're on the correct side of the arrow. Usually, like in nomenclature, positive things come first, usually before negative things. So that's usually kind of the order at which people will also write the net ionic equation, positive first, then negative ion. Again, as you can see in all of these, anything that's an ion does need a charge. So that's a super common error that people make when they go write the formulas for the ions. They do not include the charges, so make sure that you do. Question on how to use solubility rules, predict products of a double displacement reaction, total ionic equation, net ionic equation. Any questions on any of that? All right, then let's talk about acid and base reactions. Acid and base reactions also are double displacement reactions. They also fall under this umbrella of double displacement. So a more specific classification, as we'll talk about, is what is sometimes referred to as an acid-base neutralization reaction. So an acid-base neutralization reaction is ultimately still a double displacement reaction, but it is sometimes more specifically classified acid-base reactions because it involves acid and bases, basically, in this case. We talked maybe a little bit about some properties of acid and bases, but if not, let's just talk a little bit about it. Really, an acid has a sour taste. They can change litmus paper to red. They react with metals in a reaction we'll see later on in this chapter, which is a single replacement reaction. And they also are strong electrolytes that can conduct electricity. They're also weak electrolytes as well. Remember, kind of what makes something an acid, as we talked about with nomenclature, is the ability to produce H+. And for all acids, right, the cation that's involved is H+. So H+ is the cation for all acids. Bases, on the other hand, have a bitter taste. They feel slippery. A lot of soaps are bases. They also turn litmus paper blue. And they could also have strong bases and weak bases as well, which are electrolytes. What makes something a base is really the ability to produce OH minus in solution. That doesn't necessarily mean that they have OH minus in their formula, but they have the ability to produce OH minus. A lot of strong bases, as we've been talking about, do have OH in the actual formula. That's also sometimes a pretty good hint that that's like a strong base. If you actually see OH in the formula and it's one of those group 1 or group 2, probably a pretty good shot it's going to be a strong base. Again, as I mentioned before, most weak bases, ammonia has something like NH in it or nitrogen in it. A lot of weak bases have that kind of ammonia-looking part to them, and those are a lot of the weak bases. So an acid, as I mentioned before, can donate or produce H+ ions in solution. That is sometimes referred to as a proton in acid-base chemistry because hydrogen has 1 proton, 1 electron, and no neutrons. So in order for it to become positively charged, it had to lose its electron, and it only leaves it a proton at that point. We had our list there of strong acids. Again, those 6, the hydrochloric, the nitric, the sulfuric, the perchloric, the hydrobromic, and hydroiodic acid, again, are good ones to know. Again, you can use sort of a process of elimination to help you decide if it's going to be strong or weak. Because they are strong acids in solution, once again, if you took some hydrochloric acid and you dumped it into solution, you would no longer have any HCl units still together. They would completely break apart into ions. So 100% they will break apart. That is, again, really why they're considered a strong acid, because frankly, all they have to do is go for a swim and they're going to produce a lot of H+ really quickly. And again, that's really your definition of an acid, is the ability to produce H+. So that makes them a really strong acid. And again, that is different than if you took something like HF, which is a weak acid, and you pop that in there. When you throw that into your solution, you're going to mainly have the HF guys still together. It will produce a little bit of ions, but it's going to actually stay together. And that's why when we get to, like, for example, the total ionic equation, because it mainly stays together in solution, we actually don't break it apart into ions. So that's why when we have something like a weak acid or a weak base, we kind of keep it together because that is still considered an acid because it still has the ability to produce a little bit of H+ in solution, and that meets the definition of an acid, but nowhere near the amount that something like HCl, again, would produce in that solution. Bases, as I mentioned, on the other hand, do contain hydroxide. Once again, a lot of our strong bases will have hydroxide in it, come from group 1 or group 2. And as I mentioned previously as well, a lot of our weak bases are really ammonia and ammonia-based looking things like, CH3, NH2, something like that. Things that have like, a nitrogen that kind of looks like ammonia in there. So a lot of weak bases will definitely have that kind of ammonia look to them. And they probably will have a lot of times some carbons and hydrogens attached to it as well. And that's usually where a lot of those weak bases will kind of look like. So they definitely resemble having this guy in the formula is sort of a good way to recognize it. Now, the reaction of a strong acid and a strong base is referred to as a acid-base neutralization reaction. If we took something like hydrochloric acid, which is a strong acid, and we mix it with sodium hydroxide, which is a strong base. As I mentioned before, this reaction right here is still a double displacement reaction. I can recognize that because that's basically positive, negative. That's positive, negative. We're going to again switch partners here. So just like we did before, we want to put it together correctly. And essentially, when you have an acid and base and it reacts together, if you take a strong acid plus a strong base, you will always produce basically two things. You will produce water, H2O, and you will produce what is referred to as a salt. And a salt is a fancy word. I'm not sure how fancy it is, but it is a fancy word for an ionic compound, basically, something that's positive and negative together. In the case of a strong acid and a strong base, when they come together, the way that you always get the water is this way. It is always the H from the acid hooks up with the OH from the base, and that is always where the water basically comes from. So that is our double displacement, and that's basically because we're putting together H plus and OH minus. So when H plus and OH minus come together, those guys basically make water. So that is where water is basically generated. The other ion that comes together is basically what's left over. That's where we really get our salt from. So if we look at what's left over, it's our sodium that's going to go hook up with our chloride. Once again, we want to put those guys together just like normal to make sure it equals 0. And that is really where we will get the other part that will happen in this case. We will get our sodium chloride, which if we look at our solubility rules, sodium is soluble, so that should be aqueous. Water is always a pure liquid, so that's what it gets the L for. This would be our molecular equation in this case. And again, this would be obviously our water, and this would be our salt in this case. First off, any questions on that there? So we can also, for a reaction like this, because it is a double displacement reaction, we could also write a total ionic equation of what's happening. So when you dump that HCl, which is a strong acid, and the sodium hydroxide into your beaker, because they are a strong acid and strong base, they are going to 100% break apart into our ions. And those are the ions that we're going to get basically floating around in the solution. So we know that that's a strong electrolyte, which means we would have H plus Cl minus. Sodium hydroxide, also a strong electrolyte, going to break apart into sodium ion and hydroxide ion. When we come to the other side, we have water. Water is a pure liquid. So a liquid is something that you actually keep together. So in this case, H2O will stay together. And the sodium chloride, which is the salt, which is an ionic compound, we know is going to break apart because it's ionic pretty much. And that's going to give us sodium ion and chloride ion in this case. This is our total ionic equation in this case, right? And if we look at our total ionic equation, just like we did previously, and maybe we'll do that one. we could find our spectator ions. In this case, it is chloride on the left, chloride on the right, sodium on the right, and sodium on the left. These are going to be our spectator ions in this case. And just like we did before, we are going to cancel those guys out, and that's going to leave us our net ionic equation, which is H plus from the acid goes and finds the OH minus from the base, and they make water in this case. So to answer your question a second ago, obviously here we don't have a precipitate, but we do have water, which is a liquid, and that's another sort of outcome that you could have. By the way, one of the three reasons why a reaction takes place is the formation of what? Formation of water, yeah? And that is ultimately what's happening here, and that is ultimately the reaction that's taking place. Although when you do a precipitation reaction and we get a precipitate, you could actually see the precipitate. Here, when you make water, a lot of times you can't really see the water being made, right? But it is actually being made, and that is ultimately the reaction that's taking place. So an acid-base reaction or an acid-base neutralization reaction is a specific classification of a double displacement reaction that actually takes care of one of the three reasons why a reaction takes place. It is actually the formation of water. Just like we saw a precipitation reaction is a specific classification of double displacement that takes care of the making of a solid, which is again one of the three reasons why a reaction takes place. Any questions on that? You could take any combination you want of a strong acid and a strong base, and if you go through the reaction and end up at the net ionic equation, this is always the net ionic equation you're going to hit. So if you did, for example, nitric acid, which is a strong acid, and you did potassium hydroxide, which is a strong base, I could get my reaction OH and H is going to make my water. K and NO3 minus are going to come together to make my salt, KNO3. I could go my total ionic equation, H plus NO3 minus for my strong electrolyte, K plus OH minus for my strong base there. Water going to stay together. My salt here going to break apart into K plus and NO3 minus. Once again, if we look, NO3 minus on both sides, K plus on both sides, leaves us our net ionic equation of the H plus from the acid, finding the OH minus from the base, ultimately making water. So always strong acid, strong base. Again, why it's called a neutralization reaction, because ultimately it produces water. Yeah. Yeah, for example, if you had something like that, you would use since mercury is the only liquid that you have, you just had it by itself, it would stay the same. Yeah. Same thing, by the way, and we'll get into this maybe in this chapter a little bit towards the end. But for example, if you had just like solid copper, for example, in a reaction, and you had to write a total ionic equation or net ionic equation, solid copper or any metal, as if you remember from the periodic table, nobody has a charge, right, unless they hook up with something. So if you just had solid copper by itself, it'd actually just be Cu solid and just leave it just like it is. And it wouldn't actually cancel out with an ion on the other side that has a charge. So since it doesn't have a charge, they're not the same. If you had like copper on both sides and one had a charge and one didn't, they wouldn't cancel out. So it's important for the spectator ions to remember that they do have to have charges on both sides. They need to be the same and the same amount of those guys on each side for them to cancel. Yeah. Other questions? All right. So again, as I mentioned before, you could go through, and that's always, in this case, the net ionic equation you're going to hit, because ultimately that is what is happening in this reaction, is that formation of water. Here's a couple other examples like I just did there. We do get our salt. I would say probably most of the time your salt is going to be soluble in most cases. It is possible the salt could be insoluble, but very rarely I think you will come across an insoluble salt as a result of an acid-base reaction. Now, to the earlier question of maybe, what happens if we do have like a weak electrolyte? So let's say we took an acid-base reaction like this, and we took hydrofluoric acid, which we know is a weak acid, right? And we react it with sodium hydroxide, which is a strong base here, right? So once again, when we look at the reaction here, you should be able to recognize it. Remember, you could think of acids as really like ionic compounds, right? Because the cation is the positive, negative, positive, negative. So once again, I know that I'm going to get a double displacement reaction that's going to happen. And very similar to what we talked about previously, you are going to get your water from the acid and the base, right? Switching partners. That again is going to get us our water in this case. We will also get our salt in this case by the combination of the other ions coming together properly, which this is +1 and -1, which will give us NaF in this case. Solubility rules will tell us that is aqueous because it has sodium in it, right? And again, water is going to be a pure liquid. So this would be our molecular equation here, right? And we want to make sure it's balanced, which I believe it is at this point. So I think we are good on the balancing aspect of it. We could write our total ionic equation just like before. The difference, though, is when we get to this guy, because he is a weak acid and a weak electrolyte, we actually will keep it together. We will not break it apart. So what we would actually put here is HF, just like it is. We would not break it together because that is a weak electrolyte. Now, the sodium hydroxide, which is a strong base, would break apart because it's a strong electrolyte. So we would get Na plus and OH minus. Our water on the other side will still stay together because it's a liquid. And sodium fluoride is also an ionic compound, which makes it a strong electrolyte. It will break apart into Na plus and F minus. This would be what our total ionic equation would look like, a little bit different, right? Because we didn't break apart the first guy. That also has a pretty big effect on our spectator ions. What is our spectator ion in this case? It is only sodium, yeah? That is the only ion that's the same on both sides. So because we did not break apart that weak electrolyte, we actually end up with only one spectator ion in this case. And what we do is still the same. We're still going to break apart. That would be our spectator. We're still going to cancel out our spectator ion in this case. And that will leave us our net ionic equation that looks like this. HF plus hydroxide will form water and F minus in this case. Yeah. And that actually would be our total ionic equation, which looks a little bit different and also has a combination of a couple of things. We have obviously a liquid here and we have an ion as well on the right-hand side. So again, there are different sort of combinations that you could get with that net ionic equation, depending on what you start with. But because we don't break apart that weak electrolyte, we all have only one spectator ion, and we still cancel that guy out. Yeah. Yeah, so weak acids and weak bases. I would say probably your most common, most all of them that are considered weak electrolytes are weak acids or weak bases. Yeah. And again, that's why kind of knowing those 6 strong acids are good, because by process of elimination, if you happen to come across something that looks like an acid, but it's not one of those 6, you could probably safely assume that's going to be a weak acid and thus a weak electrolyte. Yeah. Other questions. So that is sort of what you would do if you had something that was like a weak electrolyte. You would want to keep it together. It will affect and really cut down the number of sort of spectator ions that you'll come across. But you still, as you see here, still cancel the one spectator ion in this case to get yourself to the net ionic equation. Any questions on any of those there? So ultimately what we just talked about here is the big category of reactions, which are known as double displacement reactions. They have more specific classifications that is a precipitation reaction that forms a solid, or an acid-base reaction that forms water. And they are responsible really for 2 of the 3 real reasons why a reaction takes place. that precipitate formation or formation of water. All right, any questions on that? All right, the next category of reactions are what are known as redox reactions. And redox reactions are what are known as oxidation and reduction reactions. So redox is short for it. Much like double displacement reactions, you could think of redox reactions as the big category of reactions, for which, as we will see by the time we're done with this chapter, a bunch of really more specific ways you could classify a reaction. So what is happening in a redox reaction? It is an oxidation or reduction reaction that's occurring. And by the way, they always happen together. So what I mean by that is if somebody is going through an oxidation reaction, they will also be somebody else will be going through a reduction. So that always happens together. You don't get one without the other, so it always does happen. The redox reactions take care of the transfer of electron need for a reaction. Oxidation means that somebody technically lost an electron or will lose an electron. There are a couple other definitions of oxidation which we won't go into too much here. You'll see it if you take organic chemistry. It involves oxygen and hydrogen either gaining or losing. But we'll focus on the electrons here. Reduction means that you have gained an electron. Now, sometimes people will remember this, that Leo the lion goes grr, loss of electrons, oxidation, gaining of electrons, reduction. Some people are fond of the oil rig, oxidizing is losing, reducing is gaining. You could put Leo the lion on the oil rig. You don't have to choose, and he'll go grr. So you could just do all four of them together, so you'll never forget. But that's one way that you can remember it. So what does it mean when somebody goes through oxidation and loses electrons? So let's just think about it logically. If I lose electrons, do I become more positive or more negative? When you lose electrons, you then have more protons, right? So you become more positive, yeah? And when you gain electrons, you now have more negative things than you do positive things. You become more negative. So for example, if you looked at like sodium metal, right, plus some chlorine gas to make a little sodium chloride in this case, I'll even balance it like I'm in chemistry class here. There we go. So when we look at what's happening here, we can basically try to figure out, what is happening with what is really known as the oxidation states or oxidation numbers of everybody. But we'll just kind of think of it like a charge. It's a little bit different, but we can think of the charge of everybody. And one of the easiest ways, I think, to figure out if something is being oxidized or reduced is you could actually just use a basic number line. And I believe there's a 0 there usually on it. And to the right of 0 are positive numbers. To the left of 0 are negative numbers. And if you become oxidized, you're losing electrons, which means you're becoming more positive. So if you look at the charge of the element on the left-hand side of the arrow to the right-hand side of the arrow, and it's actually becoming more positive, kind of moving in this direction on the number line, then that thing is going through oxidation. It is becoming more positive. If you look at the charge of the element on the left-hand side of the arrow to the right-hand side of the arrow, and it's becoming more negative, because it's gained electrons, it will be moving on the number line like towards the negative side, and that will tell you it is a reduction reaction that's happening. So for example, let's take a look at this reaction. When we have elements by themselves that are uncombined, as I just mentioned, they pretty much have no charge. Yeah, they're both 0 basically on this side. When you put a metal and a non-metal together, you get an ionic compound. That is actually when they gain a charge, right? And on the right-hand side, the sodium is +1. And on the left-hand side, or on the right-hand side, the chloride is -1, right? And that's group 7 and group 1 on the periodic table. So once again, how we could use our number line to help us is very simple. When I look at the sodium on the left-hand side, it started at 0, which is like there. On the right-hand side, the sodium ended at +1, which is heading in this direction. It is heading in the positive direction, which means that the sodium here is going through oxidation. By the way, as soon as I know the sodium is going through oxidation, by default, the chloride is getting reduced or going through reduction. I could actually do it for the chlorine as well. The chlorine on the left-hand side started at 0. So that's my sodium. This is my chlorine. On the right-hand side, this chlorine ended at -1, which means it's moving in the negative direction and it is going through oxidation. What is ultimately happening here is what we talked about when we talked about an ionic bond. This guy is sending electrons over, right? That is the transfer of electrons that is happening in this reaction. This reaction can be classified as a redox reaction because of what is happening there. As we will later see, you could also classify this as a synthesis reaction or combination reaction, basically. Question on that there. That works also really well if you maybe have the same metal on each side. So for example, let's say I had iron with a +3 on the left-hand side of the arrow and an iron with a +2 on the right-hand side of the arrow. Is this iron being oxidized or is it being reduced? So take a moment and think about it. All right, so if we look at it, the oxidation state or number or charge is the same as the charge. So that is +3 on the left and +2 on the right. I could go to my number line. +3 is like over here for my iron. And it's ending on the right-hand side at +2, which is moving to the left here, the more negative direction. This guy is actually going through reduction here, or being reduced in this case. Any questions on how to do that there? By the way, when you have a metal and a non-metal together, like we did in the first example there with the sodium and chlorine, which one should always be positive? Which one always becomes a positive charge? Is the metal, right? It's always the one giving away the electrons. So whenever you have a metal and a non-metal together, always the metal should be the one being oxidized and the non-metal should always be the one gaining the electrons, and it should be reduced. So it's pretty straightforward when you have a metal and non-metal coming together. That is always what should happen. Any questions on that there? So as I mentioned there, ultimately what is happening here is that transfer of electrons, totally missed it there, coming from here to here. And again, that is really, as I mentioned, the third reason why a reaction takes place is that transfer of electron that's happening in this case. If we look at this reaction here, we have magnesium plus oxygen makes magnesium oxide. Magnesium is by itself here on the left-hand side, so no charge. Oxygen is naturally the way it comes, uncombined, no charge. When magnesium and oxygen come together, they make an ionic compound. Magnesium is group 2, which means on the right-hand side it has a +2. The oxygen is group number 6 on the periodic table, which means it has a -2. So once again here, we can use our number line if you want to figure out what is going on. Again, if we look at the magnesium, it's starting at 0. And on the right-hand side, it's ending at +2. So that is moving in the positive direction. And as we would expect in this case, the magnesium is the one being oxidized or going through oxidation. If we look at the oxygen, it started at 0 on the left-hand side. On the right-hand side, it ended at -2. And as we would expect here, it's becoming more negative. So this is being reduced. Again, with oxidation and reduction, if you're confident about one, like I for sure think this guy's being oxidized, the other thing there has to be reduced, or vice versa. If you're like, I'm for sure this guy's being reduced, the other thing there has to be oxidized. So they always happen together. And that means you just really need to figure out one of them for sure. And the opposite thing is happening to the other one. Any questions on that there? We can also write what is sometimes referred to as half reactions that are taking place. And the half reaction in this case is this is our oxidation half reaction. Oxidation half reaction will show electrons on the product side like they are being lost or given off. And if you see a half reaction with electrons in it on the product side, it's definitely the oxidation half reaction. This is the reduction half reaction. And reduction means it gained electrons, so we will see electrons on the reactant side. And that is how you know it is a reduction half reaction, because you have your electrons on the product side there. Now, they're called half reactions because if you add those together, you get the overall reaction that's taking place. So sometimes the overall reaction is broken up into the half reactions to illustrate what is being oxidized and what is being reduced. And you'll sometimes see them written sort of like that. But much like I think we talked about maybe earlier on with electrons on one side and electrons on the other side for oxidation and reduction. Now, you may be asking, why is there 4 electrons here? And that is because each magnesium will lose 2 electrons, and there are 2 magnesiums. So that's a grand total of 4 electrons get lost by the magnesium. And there are 2 oxygens here. Each oxygen will gain 2 electrons. So that is 4 electrons. By the way, when you have half reactions, before you could add them together, the number of electrons in each half reaction does need to be the same number. And sometimes you need to multiply a reaction by a number to get them the same. The idea behind that is whatever number of electrons somebody loses should be the exact same number of electrons that's gained by the other person there in that sort of reaction. When you add them together, the electrons should always cancel out completely because they're on opposite sides of the arrow. You can kind of think of the arrow like an equal sign, so kind of subtracting them away from each other. Everybody on the left-hand side stays there, so magnesium, oxygen on the left. Right-hand side, 2 ions come together to make an ionic compound on the right-hand side. So basically you have the magnesium and the oxide coming together to make your magnesium oxide on the right-hand side. All right. We're not going to worry too much about this, but as I mentioned before, there are 2 other definitions of oxidation and reduction, which a lot of times when you get to organic chemistry, there's not a lot of metals and stuff like that happening. So a lot of times it's much easier to look at whether or not somebody gained oxygen or lost oxygen, or gained hydrogen or lost oxygen or hydrogen. So just to give you the 3 definitions, but we definitely will just focus in on the electrons here. Oxidation can mean that you lose electrons. You gain oxygen as you go from reactants to the product side of the reaction, or you lose hydrogen as you go from the reactants to the products. Reduction can mean that you gain electrons, you lose oxygen as you go from reactants to products, or gain hydrogen as you go from reactants to products. So if we take a look over here, when we look at the sulfur, it had 2 oxygens there and gets 1 more oxygen there. So the sulfur here gets oxidized. And obviously by default, the oxygen gets reduced or goes through reduction in this case. And again, we're just going to really focus on the electron aspect of it here. OChem or organic chemistry, you do a lot of the other 2 definitions of oxidation and reduction. All right, so let's talk about classifying reactions. And then now that we have sort of an idea of the 2 big categories. So once again, our 2 big categories are double displacement, which is again going to take care of basically 1 and 2 down here. in terms of reasons why the reaction takes place, and our redox reactions that take care of number 3 down here, which is our transfer of electrons. So as we saw earlier, a precipitation reaction like the one here is a double displacement reaction. So double displacement, a precipitate being made. So again, I can recognize that positive, negative, going to switch partners. And upon that switch, we get some barium chromate, which is a solid, and that is the formation of a precipitate. So again, a more specific classification of a double displacement, as we talked about, is a precipitation reaction. Again, we do get that double exchange occurring. And as we talked about a number of times up to this point, that is really what you want to look for to recognize it. No other type of reaction you'll come across, as I mentioned, will basically do that kind of double exchange of those ions. We also saw this reaction earlier as well, again, also under the double displacement category. And again, that is our acid-base reaction, our neutralization reaction. Again, the formation there of water, right, as we talked about, is ultimately what is happening in this reaction. So let's then talk about a more specific way to classify redox reactions. So these are redox reactions now, and they fall under the redox sort of umbrella. Again, if we look at this guy, that is 0, that is 0. That is naturally the way they come. When those two guys come together, that metal and non-metal, lithium is +1 from group 1, fluorine is -1 from group 7. Again, if we take a look, as we would expect, the lithium started at 0 and ended at +1, which means the lithium here is going through oxidation. The fluorine started at 0 on the left-hand side. On the right-hand side, ended at -1 and becoming more negative, going through reduction. By the way, when you're asked that question, or if you are asked that question of what is being oxidized and what is being reduced, that is always found on the left-hand side of the arrow. So that should always be reactants when you're asked that question of who's going through oxidation or who is going through reduction. Not to confuse too much, but there is something known as oxidizing agent or reducing agent, which is actually asking something different. Yeah. They're actually not. So it's really these guys here in this particular case, because they're basically the element form of these guys, right? They have no charge. So again, if you take anybody off the periodic table that is by itself, and not combined with anything else, it will always have an oxidation state of 0. We'll actually see one here in just a second where there's some charges that are happening, but it's because these are basically the elemental forms of each of these guys, right, and how they naturally come. So the oxidizing agent, in case you ever come across it, is actually the substance that gets reduced, while the reducing agent is the substance that gets oxidized. So I put this up here just to let you know that if you are asked something about the oxidizing agent or reducing agent, that is actually a different question than what is being oxidized and what is being reduced. And so, for example, in this example that we just looked at, what is being oxidized is the lithium. And the lithium, because it is being oxidized, is what's considered the reducing agent. Now, what is being reduced in this case is the F2. And because the F2 is being reduced, it is what is known as the oxidizing agent. So the way to remember it for the future probably is, if you're asked about the agent, is the opposite of the name. So the reducing agent is getting oxidized, the oxidizing agent is getting reduced. The reason that is because it is causing the opposite effect in the other thing. So for example, when lithium loses electrons, that's going to force fluorine to gain it and become reduced. So the lithium is essentially causing the reduction of fluorine and vice versa. In order for fluorine to gain electrons, it's got to cause somebody to lose electrons. So it's going to be the oxidizing agent. So the agent sometimes confuses people if you're asked about it. I don't anticipate asking too much at all about it, but sometimes books like to throw those things in and stuff like that. So for us, we're going to kind of hopefully keep it as simple as possible. We're going to, if you're asked something, what is being oxidized, we're talking about somebody losing electrons, and somebody being reduced is gaining electrons. We will kind of not ask too much about at all about the agents, but sometimes in books it does pop up. So that is what it is. So if we look at this reaction here, this reaction is a type of reaction which is known as a single replacement reaction. And a single replacement reaction is different than a double displacement reaction. And the idea here is, how do I recognize it? So in a single replacement reaction, what you will see is you will have one thing plus another thing. The one thing here can be a metal all by itself, not combined with anything else. And it would have an oxidation state of 0. This guy would actually be an ionic compound. So you'll have an ionic compound. So something that has a positive and negative. So this is different to double displacement, where we start with 2 ionic compounds. Here we start with a metal by itself and an ionic compound. And what's going to happen in this reaction is this. The metal that does not have a charge will eventually become positively charged, because that's what metals do. So it will come in actually and kick out the positive guy in the other one. And when it comes in and kicks out the positive guy, that is when the metal will then gain a positive charge and will combine with the negative guy that's there. The one guy over here that gets kicked out, he actually will get kicked out and end up with no charge. So this is what is known as a single replacement reaction. The guy coming in kicks out one person, gets a charge, and then goes the other way. You could also have a single replacement reaction that involves a nonmetal. It's set up the same way. This would be a nonmetal plus this, which is an ionic compound. Also, that nonmetal would not have a charge to begin with. When a nonmetal gains a charge, it actually will become negatively charged. So in this case, the nonmetal will actually come in and kick out the negative guy over there instead of the positive guy. It will then make a new ionic compound where it has a negative charge, and this guy that gets kicked out will come out by itself, yeah, with no charge. This is what is known as a single replacement reaction. The guy that is coming in, it needs to be more reactive than what it replaces. So whatever is coming in by itself, it needs to be more reactive than what it is replacing. If it is not more reactive, you will actually get no reaction occurring. So if it is not more reactive, you'll actually get no reaction occurring. So let's take a look at this example that we have here. We have zinc, which is a metal by itself, and it has no charge. We have hydrochloric acid, which is like an ionic compound, has a positive and negative charge. So what's going to happen in this case is the zinc's going to come in and kick out the hydrogen. When the hydrogen gets kicked out, it becomes hydrogen gas, the elemental form of hydrogen, basically, that has actually no charge. The zinc that comes in will now gain a charge of +2, and will hook up with the Cl- that's there and make a new ionic compound over here, which is zinc and zinc chloride in this particular case. This is a single replacement reaction. This is also still a redox reaction. So if we look at what's happening with the charges in this particular case, that is 0 for the zinc, that is +1 for the hydrogen, -1 for the chlorine, right? +1 H plus for the acid, right? Cl minus, right? Come together. The hydrogen on this side, which is hydrogen gas, is 0. That's naturally how it comes. The zinc chloride is an ionic compound, which is +2 and -1 in this case. And if we look at what's happening with our number line here, when we look at the zinc, it started at 0 on the left-hand side. And on the right-hand side, it ended at +2, which means the zinc is heading in the positive direction. The zinc here is being oxidized, right? How about the hydrogen? When we look at the hydrogen on the left-hand side, it actually started at +1, yeah? Which would be, say, here, +1. And on the right-hand side, it ended at 0, which means it's moving in the negative direction. And it is the hydrogen here that is being reduced, yeah? What is actually happening with the chlorine here? On the left-hand side, it started at -1. On the right-hand side, what is it? It is still -1. There's nothing happening with the chlorine here, yeah? The actual transfer of electrons is happening between the zinc and the hydrogen in this case. This is a redox reaction, and it is more specifically classified as a single replacement reaction. First off, any questions on that there? To tie together what we did with our double displacement reactions, I'll get rid of this. You can, just like we did with our double displacement reactions, which might answer a question that was asked earlier as well, we could actually write it, yeah.
Same reactive, does that mean higher charge?
No, there is what is referred to as, I go this way maybe. There is what is referred to as an activity series that you can use to help you decide if it's more reactive or not. It's the basic activity series that you might come across is actually just a list of elements, and usually hydrogen somewhere there in the middle-ish, and then you have some other elements listed above and below hydrogen. And really the idea here is if you look at an activity series, anything that is higher on the list will replace anything that is lower on the list. So for example, if you looked at the list, you would find zinc higher on the list than hydrogen. And that's why zinc replaced hydrogen in this reaction, because it's more reactive. For example, if you did the same reaction with copper and hydrochloric acid, you will actually get no reaction. And that is because the copper trying to come in is actually less reactive than hydrogen. And if you found an activity series, you'd actually find copper below hydrogen on that list. So anything that's lower on the list will not replace anybody higher on the list. So that's usually what you would kind of use to kind of guide you in terms of will that reaction take place or not. For our purposes in this class, probably I will tell you, you could just assume that most of them will occur. But if you are given an activity list like on the book or something like that, our series, that's how you'd use it. So anything higher on the list is more reactive. Anything lower on the list is sort of less reactive. Yeah.
I said like on the test, or like or kind of like the argument.
Yeah, you would probably find one if you really needed one, but probably I would assume maybe on the test I would just tell you just assume it always works. Yeah, even though it may not always be true. But yeah, so I would provide that for you, obviously, if you needed it on that. But in case on the homework or something like that, you come across it, that's how you would use that list. Again, anything lower in the list would not actually occur. That's why, for example, if you take an old penny, which is pure copper, and you file a hole in it, and you put it in some hydrochloric acid, it will be fine. If you take like a new penny, which actually is zinc inside, copper on the outside, and you file it, and you put in hydrochloric acid, the inside of the penny will actually dissolve away, and you'll have like a hollow penny left over at that point. We used to do that as an experiment at a different school. Then they're like, we shouldn't probably be destroying that much money every semester and doing that stuff. All right, so back to this equation here, which is our single replacement reaction, which falls under the redox. We can write a total ionic equation for this, just like we did with our double displacement. The zinc, which is a solid, we would keep together, obviously, and not do anything with it. Again, it does not have a charge here. The hydrochloric acid is a strong acid, so just like we did before, we would break it apart. And with that 2 would go for both of them. So we get 2 H pluses and 2 Cl minuses. On the other side, that is a gas. So just like we talked about, we would actually keep it together. We wouldn't break it apart. So this would be H2. And our zinc chloride, which is an ionic compound, would break apart. And we would get a zinc ion and 2 chloride ions in this case. And this would be our total ionic equation. And I think that was a question somebody asked. You got a little bit of everything happening in this particular one. And just like we did on previously, we would look for spectator ions. And in this particular case, our spectator ion is, not surprisingly enough, our chloride, right? As we saw earlier, nothing really happened to the chloride in this case, right? It had the same charge beginning to end. It's just hanging out to balance out the charge. There's nothing really happening here. We could actually cancel out the chloride in this case, which would be our spectator ion. And that would get us our net ionic equation, which would be zinc plus our 2 H pluses is going to go and make our H2 and our zinc with a 2 plus charge. So ultimately what's happening in this reaction, what our net ionic equation tells us is this zinc is going to offload basically 2 electrons to the hydrogen there, ion, 1 to each H plus. Each H plus will gain the electron, then come together and make H2, which is the hydrogen gas. If you did this reaction, you would see bubbles happening, and that's the hydrogen gas being generated in this reaction. The common question that you might have is, why did we not cancel these 2 out? The reason is, again, as I said earlier, the zinc on the left has no charge. It's in the solid state. The zinc on the right has a +2 charge in the aqueous state. They are not ions on both sides, yeah? Even though they're both zinc, they're not both zinc ions, so you do not cancel those out. So you can write a net ionic equation, a total ionic equation for a single replacement reaction, just like you do for a double displacement reaction. And again, you'll just have probably in this case 1 spectator ion like we saw in this example. Question on that there. Also, just to clarify, just to make sure, with double displacement reactions, there is no electrons being transferred. There is no change in the charge of anybody from the left-hand side to the right-hand side. So when we look at our double displacement reactions, the charges on the left are the same charges they have on the right. There is no transfer of electrons happening. Only in redox reactions, we're essentially getting these transfer of electrons. So redox reactions, transfer of electrons, a specific classification of a redox, single replacement reaction falls under that category. Another classification of reactions that fall under redox reactions is combustion reactions. And when we talk about combustion reactions, there's really 2 types of combustion reactions we talk about. I would say probably 99% of the time in your conversation you're having, while you're having conversations about combustion reactions, I don't know. But in your conversation about combustion reactions, most people are probably thinking about the organic combustion reaction, like what happens when you light your Bunsen burner, which is an organic compound plus O2, CO2 plus water. So an organic compound is carbon, hydrogen, oxygen perhaps. And if you have an organic guy, you got O2, CO2, and water is always what you will get on your product, unless you have what is referred to as an incomplete combustion reaction, in which you would get carbon monoxide instead of carbon dioxide. But most of the time, it's going to be carbon dioxide and water. Here's what you get when you light your Bunsen burner: methane, carbon and hydrogen, O2, CO2, and water. Here is propane. Organic compound, carbons and hydrogens, O2 on the left, CO2 and water on the right. If you see O2 on the left, CO2 and water on the right, that is definitely a combustion reaction. Don't even think twice about it. Is this combustion reaction for sure? When you see those 3 things together, that on the left, these 2 on the right, definitely a combustion reaction for sure. Like I said, that is probably the most common combustion reaction that most people would think about and talk about. But there's actually just a general definition of combustion, and all you have to have for a combustion reaction to happen is this. All you need is O2 being present. So if you have a reaction that technically has O2 present, it is technically a combustion reaction. So if you think about that reaction we saw earlier, that magnesium one, where we had the oxygen, makes a little magnesium oxide here. A little 2 there. This is a redox reaction, right? Because it falls under that umbrella, 0, 0, plus 2, minus 2. This contains oxygen, which means it falls under the combustion reaction as well. And that is all you need is just, technically speaking, O2, oxygen gas on the left-hand side of the arrow, and you could classify it as a combustion reaction. I would say most people probably wouldn't classify this particular reaction as a combustion reaction, but it technically is. There's a better classification can happen. Perhaps what you might be seeing right now and what we are talking about here is you can take the same reaction and classify it multiple ways depending on sort of what you're looking at. Just like this one here, we could classify it as a redox reaction. If we're thinking about electrons and transfer of electrons, we could also classify it again as a combustion reaction because it has O2 in it. So there are different ways to classify the same reaction. And again, just like we saw with double displacement reactions, we could classify an acid-base reaction as an acid-base reaction, or we could classify as a double displacement reaction as well. So multiple ways that you could kind of do that. Another type of reaction that we come across is a synthesis or combination reaction. This also is a redox reaction. How do you know you have a synthesis or combination? It is pretty simple. You have two things that make one thing, yeah? Hence the word combination, right? So basically two things make one thing is a combination or synthesis reaction. I see H2 and O2, that is two things make one thing, combination or synthesis reaction. Sodium, chlorine, two things make one thing, combination reaction, right? Again, they are also redox reactions. That is, if you're not sure here, our water formation, which is two things make one thing, which is a combination or synthesis reaction. If we look at what's happening here on the left-hand side, that is hydrogen by itself, 0 charge. Oxygen by itself, 0 charge. When water comes together, if you remember, we made water by taking H plus and OH minus, right? So essentially that is what we have charged here. So if we look at the hydrogen, it started at 0 on the left. On the right-hand side, it ended at +1, which means it's becoming more positive. It is being oxidized. By default, the oxygen is being reduced in this case. And again, if you look at the oxygen, it started at 0, ended at -2, becoming more negative. So that first one is a redox reaction. It is also can be classified as a synthesis or combination reaction. And the same thing with what we saw down here. We saw that as a redox reaction, obviously, and it could also be classified as a synthesis reaction. If you take the one we just wrote on the previous page, this guy right here, we saw this as a redox reaction. We just classified it as a combustion reaction, right? It also very much looks like two things make one thing, right? You could classify this guy as a synthesis or combination reaction, yeah? So that one reaction could actually be classified in 3 different ways. Which one should you choose? Probably whichever one you're kind of looking at. I would say probably most people would choose synthesis or combination for this reaction. But again, the other two are definitely not wrong. They're correct classifications of that reaction. Any questions on any of that there? The last type of reaction here is basically the opposite of a synthesis reaction, and that is a decomposition reaction. So in a synthesis reaction, we kind of put it together. In a decomposition reaction, we break it apart. We have one thing that makes multiple things. We kind of break it apart. Also a redox reaction here, yeah? So this is also a redox reaction, yeah. You need to know the names and ways to classify them, yeah, for sure. So if we look at this here, if we take an electrical current through water, which you will do perhaps, just a 9-volt battery will do it maybe. It will break apart water into its elements. So one thing makes two things here. Going in the opposite direction, by the way, the opposite thing happens when we look at this decomposition reaction. Just looking at the elements involved there. That is +1, that is -2, that is 0 and 0. Going in this direction, it is actually the hydrogen in this case that starts at +1 and ends at 0 that is getting reduced. So it's actually the hydrogen here that gets reduced going in this direction, and it's the oxygen that gets oxidized in this case. Oxygen in this case starts at -2 and ends at 0. So it's actually opposite. It is opposite of what happens in the previous one we looked at because it is the reverse reaction. So in this reaction, the hydrogen actually gets oxidized and the oxygen gets reduced, but going in the opposite direction, those things actually switch around as well. So in this case, going in this direction, reduce for the hydrogen and oxidize for the oxygen. Now, if you have something like carbonic acid, for example, carbonic acid will very quickly break apart into water and CO2. Again, one thing makes multiple things. So decomposition is really like basically the direct opposite reaction of synthesis. Synthesis, you put it together. Decomposition, you break it apart. Questions on that there? So just to summarize, so everybody again is on the same page. We talked about two big classifications of reactions, double displacement, which is again our two ionic compounds coming together, always going to switch partners here and make two new ionic compounds on the other side. It takes care of precipitate and water being made. More specific classifications of double displacement reactions is a precipitation reaction, where obviously you do get a precipitate formed. And a more specific classification of double displacement reactions is an acid-base neutralization reaction, where you basically form water, right? So again, those are the more specific classifications of double displacement. As I mentioned a second ago, absolutely no change in charge, no electrons being transferred here. Everybody stays the same charge on the left-hand side and the right-hand side of the arrows. Our other big classification is our redox reactions, which involves oxidation or reduction. That takes care of our electrons being transferred. Underneath our redox sort of umbrella, we have more specific classifications. We have our single replacement reaction that we could recognize by having either a metal or a non-metal by itself with no charge plus an ionic compound. And again, if this was a metal, it would come in and kick out the positive guy. If it was a non-metal, it would kick out the negative guy, making a new ionic compound on the other side, and that guy comes out by itself with no charge. So remember, single replacement, that is how you can recognize it. It looks different than what you see with a double displacement here. We also have combustion reactions, which fall underneath this. Basically, you need O2 to be present for it to be a combustion reaction. And again, in most cases, you will have an organic compound that's carbon, hydrogen, maybe even oxygen in there, plus O2, CO2, and water. Again, those are the three things that if you see together in that arrangement, definitely a combustion reaction. Also, again, a redox reaction that's happening. We also have a synthesis or combination reaction. That again is like we just saw two things make one thing. And again, like we saw there, water plus oxygen, hydrogen plus oxygen makes water. Or even our sodium plus chlorine makes sodium chloride. 2 there as well. And lastly, we have a decomposition reaction where one thing breaks apart into two things. And again, as we saw, you could do the electrolysis of water, run that electrical current over it, and it will break it apart into hydrogen gas and oxygen gas. Again, everybody on the right-hand side falls under the umbrella of redox. Everybody on the right-hand side, ultimately what is happening is a transfer of electrons is basically what's happening there on that right-hand side. And again, those are our more specific classification of reactions that fall under the redox umbrella. All those reactions up there on the screen basically account for all the reactions that you'll come across. And ultimately, it all boils down to three things. Either you make a solid, you make water, or you transfer electrons is essentially what's happening. Any questions on that there? That is chapter 7.